Hello everyone. In this video we are going to talk about the triaxial shear test, which is considered a complex test that can be done on the soil in the lab to calculate the shear strength parameters of the soil. Well, before dealing with a solved example on the triaxial shear test, we just will summarize the test in a few steps. First of all, this is a device which is used for the triaxial test. Basically, you have here the soil sample, which is saturated with water, and it's surrounded by a rubber membrane so that the water doesn't get out of the soil sample. This is a cell where you can pour inside the cell some water under pressure. So you can allow some water under pressure to get into the cell so that the water will apply a pressure on the soil sample. This pressure will be in all directions so that this test is called triaxial test. In this test you can measure the excess pore water pressure, and the soil sample is connected with a tube where you can control the drainage of water from the soil sample through a valve here. You can find a valve here which you can use to allow the drainage of water outside of the sample upon loading. So let's take a quick idea of the triaxial test. First of all, let's just assume that we have a soil sample here. The soil sample is saturated with water and is surrounded by a rubber membrane. It has got some porous discs above the soil sample and below the soil sample, and it's connected to a tube where you can control the drainage of water through a valve. So the first step is to allow some water under pressure to enter the cell so that you have applied a cell pressure on the soil sample in all directions. It's a triaxial pressure, it's a triaxial stress. This stress is called sigma 3, and it's called confining pressure, or it's called cell pressure, or it's called water pressure. Cell water pressure. It's a pressure from outside the soil sample on the soil sample from all directions, so that the soil sample, it can be said that the soil sample is being squeezed under these pressures from all directions. In this step, we call this step the consolidation phase. This step is mainly called the consolidation phase. So in the second step, an additional axial load will be applied. We have here an arm. We can apply a vertical load. It's an additional axial load because the soil sample is already subjected to an axial stress which is called sigma 3. However, now we apply a new additional stress. I will write it in a different color. It's called sigma deviatoric. Its value at failure is called sigma d, or sigma deviatoric. This axial stress begins from a 0 value and is increased up to failure. However, the value of sigma 3, the confining pressure, is constant during the test. So you now have two types of stresses: confining pressure at triaxial pressure in all directions, which is called sigma 3, and it's constant during the test. It may be 50 kilopascal, 100 kilopascal, or whatever. And you have applied a new additional stress, which is sigma d. It's an axial additional stress. This phase, or the second step, is called shearing phase. So when you apply some additional axial loads which are increased from 0, or an axial stress which is increased from 0 to a value of sigma d, this phase is called shearing phase. So now if you want to calculate the value of the total axial stress, you can say that the total axial stress at failure, it can be denoted by sigma 1, and it's the summation of two components, which are sigma 3 and sigma d. You must know that sigma 3, which is the cell pressure or the confining pressure, it's called minor principal stresses, while sigma 1, which is the total axial stress on the soil sample, for now it's called major principal stresses. These stresses are called principal stresses because they are applied on some planes or a surface which doesn't have any shear stress on it. This surface, which is the vertical surface of the soil sample, which is in the shape of cylinder, or the upper surface on which a vertical or axial stress is applied, these surfaces are not subjected to any shear stresses, so these surfaces are called principal surface or principal plane. And consequently, any normal stresses on these principal planes are called principal stresses. So you have sigma 3, which is the minor principal stress. You have sigma 1, which is the major principal stress. So we will repeat the test at least 2 or 3 times. For every test, you apply a constant value of sigma 3 and sigma 1, which is sigma 3 plus sigma d. For every test, you will apply a new sigma 3 value. For example, for the first test, you can use a sigma 3 value of 50 kilopascal. For the second test, you can use sigma 3 value of 100 kilopascal. For the third test, you can apply a sigma 3 value of 200 kilopascal. So that in every test, you will have a new value of sigma 1, which will increase by increasing the value of sigma 3 through the tests. So now you will draw more circles. It's easy to draw a Mohr circle using the major and minor principal stresses. All you have to do is to draw the relationship between tau, which is the shear stress, and sigma n, which is the normal stress. How can we draw a Mohr circle? Well, the Mohr circle, it's one half of a circle. Its diameter is equal to sigma d, or the deviatoric stress. This point, it's a normal stress, sigma n. So this point is sigma 3, the minor principal stress. This point is the major principal stress, sigma 1. So if you already know the value of sigma 3, let's say it's 50 kilopascal, and sigma 1, let's say that it's equal to 150 kilopascal, then you can calculate the mean or the average of these two values. It's 100 kilopascal. It's the center of your circle. it's 100 kilopascal here. This is the center of your circle. Then you can draw your circle by knowing that the radius is equal to 50 kilopascal. The radius of the circle is equal to sigma d over 2, which is 50 kilopascal. So once you know the value of sigma 3 and sigma 1, you can find the average of these two values and you can draw your Mohr circle. You will draw the second Mohr circle in the same way, just like the first Mohr circle, by knowing the new values of sigma 3 for the second test and sigma 1 for the second test. By knowing the values of the new sigma 3 and sigma 1, you will draw the second Mohr circle. Then you will plot a tangent. You will plot a tangent to this Mohr circle. You have to draw one tangent to both circles. So let's say that this is the tangent. This is your failure line or failure envelope according to Mohr-Coulomb approach. Then in this way you can find your intercept on y-axis, which is the value of c, and you can measure the value of the angle between the failure envelope and the horizontal axis. This angle is phi. So in triaxial test you have three types. In triaxial compression test you have three types. These types are based on a main fact. I will talk about this fact right now. The soil sample on which you apply the test, I have already mentioned that the soil sample is connected to a tube where you can control the drainage of water outside of the sample through a valve. So you are free, you are totally free to allow the water to move out of the sample by opening this valve, and you are free to close the valve, and you can therefore prevent the water from moving out of the sample. So the first type of the triaxial test, it's called unconsolidated-undrained triaxial test. In this test, the valve is always closed. Whether you are in the first phase, consolidation phase, where you apply the cell pressure of the sample, which is sigma 3, the valve is closed and drainage of water is not allowed. And if you are in the second phase, which is a shearing phase, in which you apply an additional axial stress, so that the total axial stress in this phase is sigma 1, in this phase the valve is also closed and the water is not allowed to move out of the soil sample. In fact, you have to know that since the soil sample is being squeezed under the stresses of sigma 3 and sigma 1, the water wants to move out of the sample. It wants to escape from the load. However, if you close the valve, the water cannot move out from the soil sample, and therefore excess pore water pressure delta U will be generated. The water wants to get out of the soil sample, but it can't. So an excess pore water pressure is generated in this test. In fact, as a matter of fact, this test simulates the field conditions where you have a soil profile of saturated clay being loaded. When you have saturated clay in the field and you have a foundation on the ground surface. So you have here a foundation under a load which is increasing, and you have here saturated clay. The water in this saturated clay, the clay has a very low coefficient of permeability, so that the water can't move freely. Practically, the clay can be considered impermeable because it has a very low coefficient of permeability, at least in the short-term conditions. This is for the short-term conditions. After 1 month, after 2 months, after 3 months, at the short-term conditions, once you have some foundations loaded over saturated clay, the water can get out of the clay, the drainage of water is not allowed, so that the unconsolidated undrained simulates and replicates these field conditions. So this test is mainly done on saturated clay. It's not done on sand at all. Unconsolidated undrained test is not done on gravel or sand or any coarse grained soil. When you draw your Mohr circles, you will find that the Mohr circles give you a horizontal failure envelope. The tangent will be a horizontal line, and these Mohr circles are in terms of total stresses. Since you have a value of excess pore water pressure, so that the total stress here it's about sigma it's effective stress. It's the effective stress plus the pore water pressure. So since you have new values of pore water pressure which are generated in this test, you must say that these Mohr circles or the failure envelope is in terms of total stresses. The value of the intercept on y-axis is called C sub u. It's for C undrained. Just I want you to know that this is an undrained condition. The water is not allowed to move out of the sample. Well, in the second test, consolidated-undrained test, here in the first phase, which is the consolidation phase, where you apply a sigma 3 a cell pressure on the soil sample, the valve is opened. Here the valve is opened, so that during the application of the cell pressure, the triaxial stress sigma 3 on the soil sample, the water can move out of the soil sample. The water can escape from the load. However, in the second phase, which is shearing phase, in which you apply an additional axial load up to failure, up to the value of sigma 1, the drainage of water is not allowed because you have closed the valve. So in this phase the valve is closed. So it's a mix. You have two phases. In the first phase the valve is open, and therefore the test is called at first consolidated. Then in the second phase the valve is closed, so it's called undrained. So it's consolidated undrained. In the first phase the valve is open, in the second phase the valve is closed. So pore water pressure is usually measured in this test, so we will be able to draw two failure envelopes. The first failure envelope, which is the dashed one, is called effective stress failure envelope, or the failure envelope in terms of effective stresses. This means that this failure envelope will be drawn in terms of sigma 1 prime and sigma 3 prime. On the other hand, the other failure envelope, it's the total stress failure envelope, or the failure envelope in terms of total stresses. This means that this failure envelope is drawn in terms of total stresses, which are sigma 1 and sigma 3. And you must know that according to Triaxial's principle of effective stresses, you must know that sigma 1 is equal to sigma 1 prime plus the generated pore water pressure, and sigma 3 is equal to sigma 3 prime plus the generated pore water pressure in the test. So if you have the values of sigma 3 and sigma 1, you can draw your Mohr circles and you can draw your failure envelope in terms of total stresses and get phi. However, if you want phi prime, or if you want the phi in terms of effective stresses, you must compute the value of sigma 1 star and the value of sigma 3 star by subtracting the value of the pore water pressure from the value of total stress. So sigma 1 prime is equal to sigma 1 minus u, sigma 3 prime is equal to sigma 3 minus u, and after that you can draw your Mohr circles in terms of sigma 3 prime and sigma 1 prime and draw your tangent. Then this is the failure envelope in terms of effective stresses, and therefore you can get your phi dash. The diaphytoric stress, it's only one stress, sigma d. There is no sigma d in terms of effective or total. It's one value, which is sigma d, and it can be used between sigma 3 and sigma 1, as we have already known. Sigma 3 plus sigma d, it's equal to sigma 1. This is a fact. And also sigma 3 prime plus sigma d is equal to sigma 1 prime. So it can be used, and its value, we can use the value of sigma d to compute sigma 1 or sigma 1 prime by adding the value of sigma d to the value of sigma 3 or sigma 3 prime. The third test is a consolidated drain test, and of course in this test the valve is always open. Whether you are in the consolidation phase or you are in the shearing phase, the valve is always open and the water is allowed to get out of the sample, so no water pressure is generated. The water is totally free to move out of the soil sample, so no excess pore water pressure is generated at all, and it's equal to 0. Therefore, in this test, it's always true that sigma 3, it's equal to sigma 3 prime, and sigma 1 is equal to sigma 1 prime, because no generation of pore water pressure takes place. There is no excess pore water pressure. It's equal to 0. So we always call this failure envelope effective stress failure envelope. It's always said that this failure envelope is in terms of effective stresses, since there is no pore water pressure generated at all in this test, because the valve is always allowed to, or the valve is always open in the test. This test is this test represents mainly the sand or the coarser grained soils, and it represents the clay on the long run. Whether you have sand in your soil profile in the field, or you have clay and you are doing some analysis for the long run, For both cases, whether you have sand or gravel or you have clay but you are doing some analysis for the long run, for both cases, in the field the water is allowed to move. The sand or gravel has a large or a big coefficient of permeability, so from the beginning, once you have built your foundation on the soil, the water will not take any shears from the load, it will not carry any stresses, no excess pore water pressure will be generated. On the other hand, the clay or the cohesive soils, in the short run, the water is not allowed to be drained and no drainage of water takes place in the short run. However, on the long run, drainage of water takes place because after 15 years or after 20 years or after 30 years, although the clay has a very small coefficient of permeability, the water will be able to be drained, but after a long period of time, maybe after 10 years, 15 years, 20 years. So this test can be done on clay, which is consolidated-drained test. This test can be done on clay on condition that you want to have the C dash and phi dash on the long run for the clay. That's all. Now we have to deal with our solved example, and it's about consolidated-undrained triaxial test. And the consolidated-undrained triaxial test, it was the second type in my description in the last slide. It was done on a normally consolidated clay. So as a matter of fact, you must know that for the normally consolidated clay, it's well known that the value of effective cohesion, or C dash, which is cohesion in terms of effective stresses, is equal to 0. However, there is a value of C undrained, which is in terms of total stresses. It may be 20, 50, 60, 100, 150 kilopascal. This is according to the state of the clay. If the clay is soft clay, the value of C undrained may be 20 kilopascal. If the clay is stiff clay, the value of C may be 80 kilopascal, and so on. So for normally consolidated clays, generally you have a value of C undrained, which represents the shear strength in the short run, and this is in terms of total stresses. On the other hand, you have C prime, which is equal to 0, which is obtained on the long run, and it simulates the effective stresses, or it's calculated in terms of effective stress. So here you have a consolidated-undrained triaxial test, which is done on a normally consolidated clay. You have done the test 3 times. For the first time, the applied cell pressure sigma 3 was equal to 100 kilopascal. For the second time, the pressure was equal to 200 kilopascal, and for the third test, the C sigma 3 was equal to 300 kilopascal. Sigma D, the deviatoric stress at failure, was found to be 137, 210, 283 respectively. As we have just said, or as we have just mentioned, in this type of triaxial test, you can measure the generated excess pore water pressure, and it was 22 kilopascal, 86 kilopascal, and 147 kilopascal. So you are required to determine the cohesion and the internal angle of friction in terms of effective stresses. So if you want these values in terms of effective stresses, you must know the value of sigma 3 prime and sigma 1 prime. However, the given data, you have only the value of sigma 3 as a total stress and the pore water pressure and sigma d. So we will use some equations. The first one, you want sigma 3 prime. You have sigma 3 total stress and you have pore water pressure, so that you can say that sigma 3 prime it's equal to sigma 3 minus u. This is the first equation. You have sigma 3 prime. But what about sigma 1 prime? Here you can use the value of sigma d. If you have the value of sigma 3 prime, you can say that sigma 1 prime it's equal to sigma 3 prime plus sigma d. This is the second equation you will use here in this problem. So you have these two equations. You will obtain the value of sigma 3 prime at first, then you will compute the value of sigma 1 prime by adding the value of sigma d to sigma 3 prime. Then you can plot these values in this table. Sigma 3 prime, it's 78 for the first test, 114 for the second test, 153 for the third test. For example, the 153, this value is equal to the cell pressure sigma 3 was 300 minus the pore water pressure 147. Sigma d, it's constant, it's one value. There is no sigma d and sigma d prime, it's one value. So if you added the value of sigma 3 prime to sigma d, sigma 3 prime plus sigma d, sigma 3 prime plus sigma d, you will have the value of sigma 1 prime. Now you have the values of sigma 3 prime and sigma 1 prime for the three tests. So you can plot your Mohr circles and you can come up with the value of C dash and phi dash, C prime and phi prime. So since this is a normally consolidated clay, and we have just said that for normally consolidated clay, C prime is generally is equal to 0 or it's close to 0. This is from the knowledge in soil mechanics. This is a fact for normally consolidated clay, so that when you draw your tangent to your three Mohr circles, the tangent, it's expected that the tangent will pass through the origin point, so that the intercept on the y-axis is equal to 0. However, if the clay was over-consolidated clay, for over-consolidated clay, the C prime is not equal to 0, it's more than 0. It can be 20 kilopascal, 50 kilopascal, 40 kilopascal, so your tangent will not pass through the origin point. So in our problem, we have a normally consolidated clay, so this tangent is correct and it passes through the origin point, so C dash or C prime is equal to 0. But what about the value of phi? So if you have your compass, you can measure this angle using your compass, or if you don't have a compass, you can take any 2 points on this line. Any 2 points, you can take any 2 points and measure the slope through the equation delta y over delta x. It's equal to the slope of the straight line. Once you measure the slope, you can take the tan inverse of the slope and you can come up with the value of phi dash, and you will get it at 29 degrees.